To the lecture series on signals and systems. This is a continuation one lecture for the elementary signals that what we are discussing. In this lecture, we will study about a unit parabolic function. And the continuous time unit parabolic function P of t is defined as P of t is equal to t square by 2 for all t greater than or equal to 0. And it is 0 for t less than 0. Okay, therefore, P of t can be represented as a one-sided signal in terms of unit step as t square by 2 into u of t. And the graphical representation of P of t is given as P of t for the y-axis and t is your time axis, the horizontal axis. And you could see the shape of your P of t, that is a unit parabolic function, will be something like this. Okay, for 0, you could see this as some parabolic function actually. Okay, for all 0. That means if at all it is equal to 1, it becomes at 1 it is equal to the amplitude is equal to 1 by 2. And similarly at 2 it is equal to at 2 it is equal to 2 square by 2, that becomes 4 by 2, which is equal to 2 itself. And similarly at 3 you could see that it is equal to 9 square by 2, that becomes 3 square by 2, that is 9 by 2, which is equal to 4.5, and so on. You could see a parabolic signal which is clearly increasing. And the unit parabolic function can be obtained by integrating the unit ramp function or double integrating the unit step function, as that what we have seen in the case of unit ramp and unit step relations. Similarly, now the parabolic function P of t can be represented as integral of r of t dt. Since your r of t is can be represented in terms of u of t as an integral over it, therefore I can also write it as double integral over u of t dt. And since you know about r of t, which can be written as integral t dt, I can write this as t square by 2 for all t greater than or equal to 0. As your r of t as well as u of t exists only for t greater than or equal to 0, similarly p of t will be also existing for t greater than or equal to 0. And the ramp function can be represented as the derivative of d by dt of p of t, the parabolic function. And you can also see that the step function u of t can also be represented as the double derivative of d square by dt square of p of t. This can be taken directly from this above relation itself. And similarly, the discrete time unit parabolic sequence P of n can be defined as P of n is equal to n square by 2 for all n greater than or equal to 0, and it is 0 for n less than 0. And when you consider the discrete time version of this sequence, you could see that it is equal to at 0 it is 0, at 1 it is equal to 1 by 2, at 2 it is equal to 2 itself, 0, 1, 2, at 3 it is equal to 4.5, and so on. Therefore, the locus of all these points will be representing a parabolic function, and you could see this is your P of n for various values of n. Similarly, now we shall study about another elementary signal that we come across in the signals and systems, that is about a sinusoidal signal. Sinusoidal signal, this is a general signal we generally tend to use many a times as an example for many kinds of operations as well. And therefore, let us discuss about the sinusoidal signal. A continuous time sinusoid signal, in its most general form, it is given as x of t is equal to a sine omega t plus phi. Here, A represents the amplitude of the signal, omega represents the angular frequency, T represents the time variable, and phi represents the phase angle just in radians. And if we consider the waveform of a continuous time sinusoid, it will be something like this. I would like to show a general form of a sinusoid, uh, which is slightly out of phase. That is, it's not the phase is not equal to 0 in this case, and you could see uh, generally the sinusoidal signal is something like this. Okay, let us consider this is our a sinusoidal signal which is represented as x of t, and you could see here the amplitude A is generally written as A. The amplitude of the signal is A, and similarly, as I said, if at all we consider the time period of the signal, that is for a full cycle, we could see that t is equal to 2 pi by omega. Generally, we write this as omega is equal to 2 pi f from the angular frequency definition, and you could also see that this can be written as 2 pi by t, or else t is equal to 2 pi by omega. This is how I have written this as capital T is equal to 2 pi by omega, and this actually represents the phase, the phi phase of this particular signal, where it is slightly deviating from the zero phase. And if you would like to represent a discrete time version of this signal, you could see that it takes the same form, and you can write it as x of n is equal to a sine omega n plus phi, where a represents the amplitude, omega represents the angular frequency, n represents the discrete time variable, and phi represents the phase angle. And the period of a discrete time sinusoidal sequence can be taken as n is equal to 2 pi by omega into m, where capital N as well as capital small m are integers, capital N and m are integers, and all continuous time sinusoidal signals are periodic, but discrete time sinusoidal sequences may not be periodic depending upon the value of this omega. Okay, we shall discuss about this clearly whenever we are discussing about the classification of signals too. And the graphical representation of a discrete time sinusoid can be seen in this way. This might be in this way, and so on. Okay, this is your x of n, and this is your time axis. It takes the shape of a sinusoidal signal. Whenever we plot this, it would be representing a full cycle of a sinusoid.